In the previous class, we have covered the concept of hashing, right? What is the meaning of hashing? Hashing is a kind of a technique which you use to store and retrieve the data. In an efficient way. How we are going to store and retrieve the data in an efficient way? By applying various kind of hash functions. What is the meaning of hash function? Hash function is a kind of a mathematical function which used for to convert our key into the respective index portion, right? So while discussing this particular concept, we have seen various kind of mathematical functions. Those might not always provide the efficient solution, right? Based on that, we have discussed separate chaining is one solution, and open addressing is another kind of solution, and the bucket hashing is another kind of solution, right? So the order in which you are trying to store the data, in the same order you are going to retrieve it. While trying to store the data, you required, let's say, three iterations. While retrieving data, definitely required three iterations or not? Definitely required three iterations. Am I right? If I want to store a data at a particular position, if I want to store a data at a particular free slot, trying to find out requires three iterations. Similarly, trying to find out an element, whether it is available or not, I require definitely minimum three iterations. Or until you found empty slot. Am I right? The same scenario, if you are able to compare, you can get the complete idea. Okay, now, so this is the logic behind hashing concept. So here, so this hashing technique is majorly works for how to store and how to retrieve the data. Fine. So now in today's session, we will try to move with the further concepts. For example, I have 1 lakh records. 1 lakh records. Those might be either your roll numbers or your names, whatever it might be. I wish to store them. For example, I have stored it in an unsorted array. Trying to find out an element in the 1 lakh records. What is the time complexity? Big O of n, obviously, right? The element might not be available at all. Or what might be another solution? You can able to store it in an sorted array. Then time complexity will be big O of log. Right? So these time complexity I am trying to discuss with respect to the concept of what? If you are going to use the internal data structure as arrays, the time complexity will be big O of n for unsorted array, big O of log n for sorted array. The same concept I can able to implement with another concept, with another data structure, internal data structure, which we call it as linked list. If you are going to store the data in linked list format, right? Whether you might be stored in a sorted data format, or you might store in unsorted format. What will the time complexity for linked list? Big O of n. Why even if it is a sorted linked list, you are not going to get big O of log n? Because in linked list, random access is not possible. So we are going to get time complexity of big O of n. Now the question is, do we have any solution which will definitely get a time complexity of less than big O of n in linked list? The solution for that is trying to represent your data in the trees format. Okay. Sir, what is happening in trees? I mean, in general, if you take the real world data, I mean, so far you are trying to store the data in which format? You are trying to store data in some straight line format. Am I right? Some linear format. For example, if I take an array, 5, 1, 4, 2, 3, is it a linear format or not? Yes. Or if I take some kind of linked list, 5 is connected to 1, 1 is connected to 4, 4 is connected to 2, 2 is connected to 3, whatever it might be, the data is again is in which format? Some straight line format, or I can say it as linear format. But because of the way you have stored the data, you are not able to achieve your requirement. Right? The simple reason is you cannot able to skip n number of elements. If the data is in some sorted format, are you capable to skip n number of elements or not by applying the binary search algorithm? If the data is in sorted format, you can able to skip every time half of the elements because of by applying some kind of binary search algorithm. But if you go with the linked list concept, is there any solution to randomly access the data? No. That's why you are always going to get a time complexity of big O of n for the worst case. So the solution is, if you want to get a time complexity of less than big O of n, can we able to arrange this data in some other format? That format generally we are following already, hierarchical order. Right? For example, if you have a laptop, right? In our laptop, you have the drives, various kind of drive, right? If you go for computer, in computer you might move to the respective like 2025-26, and in that DSM2, in that you can go for animations, images, mocks. So is it easy for you to traverse from one folder to another folder? If you place all folders in one drive, right? So it might be 100 folders also at one location. Trying to fetch one folder from 100 folders, is it a difficult task? Definitely. But instead of placing all 100 folders at one location, if you are able to segregate them into different subfolders, which one is the easiest one? Trying to place it in some kind of segregating some subfolder format definitely is the easiest one. That is what I am calling it as hierarchical order. Right? In general, in our campus, how we are going to raise a problem? If you are facing any problem, how we are escalating it? First, you might escalate it to the HOD, then Dean, then AO, then you go for Director. If it is not there, then you go for Chancellor. Like that, you will escalate the problem. Right? You are not going to directly jump into the top level. Right? Then, trying to follow the hierarchical approach definitely give the best solution for you. Right? Because for a particular step, you might skip n number of elements. That's where the simple solution is hierarchical. If you are able to arrange the data in some hierarchical format, definitely you will get the time complexity of big O of n. Right? So, for example, just now I mentioned that if you say it's a kind of your computer contains 4 folders. One is D drive. So it might start with C drive, right? C drive, D drive, E, and F drive. And in D drive, again you might have a folder name called, let's say, RGKT. And you have one more folder called, let's say, workshops. Again, workshops can be of 2 folders again, let's say. One will be virtual, another one is offline workshop, something like that, right? So if you are able to observe, this is what we call it as hierarchical file system representation. So I can write it clearly. So we can call it as hierarchical file system representation. What is the meaning of file system representation? How you are going to segregate the files in the system. So we call it as hierarchical file system. So if I want to move to a particular file related to the offline workshops, if I want to move to particular folder related to the offline workshops, so do we need to visit again E drive and all those things? No. You can just directly move to the computer to D drive to workshops to offline. This is the advantage of mentioning your data in some kind of hierarchical format. So that, are you going to skip the remaining all folders or not? C drive, E, F, RGKT, virtual and all those things? Yes. This is where you will definitely get a time complexity of big O of less than big O of n, which we can say it as big O of log n. Big O of log n. Sir, I can't exactly directly say here it is big O of log n, but you can able to achieve it a time complexity of less than big O of log n. Less than big O of log n. Okay. So this hierarchical representation we call it as a tree. We call it as a tree. Okay. So if I say something, what is a tree? So do you heard these classifications in the starting class of our data structures? We have classified trees, data structure, arrays, linked list, right? Arrays and the linked list will be comes under what kind of data structures? Linear data structures. Whereas coming to trees, a tree is a non-linear data structure. A tree is a non-linear data structure. Why we are calling here tree as a non-linear data structure? So when we say that anything as linear data structures, a node have only one suffix and one prefix. That's it. If a node is connected with only one suffix and the one prefix, then we call it as linear data structures. If you take the example of arrays, 4 is prefix with 1, 4 is suffix with 2. That's it. If you take here the linked list, 4 is suffix with, prefix with 1 and suffix with 2. That's it. If it is connected to only one element, I can call it as linear data structure. What about the trees? Trees can connect it to more than one element. It can suffix with more than one element. For example, if you take here D drive, is it contains suffix with more than one element or not? Yes. Then we call it as non-linear data structures. So a tree is a non-linear data structure where data is arranged in hierarchical order. Hierarchical, right? So in other words, I can call tree as, so you should not write in the exam, we can call it as inverted tree. We can call it as inverted tree. I mean, in general, if I take any kind of a tree, so you can observe, right? It's a kind of a tree. So in this tree, we have branches are there, right? So for this branch, there might be a kind of leaves also there. Okay. So if you observe this bottom part, what we call root. We call it as a root, and this one leaf, or I can call it as leaves. The same scenario, the real world same scenario, what you are observing in a tree, if you make it inverted, you will get hierarchical file system. You will get the data structure tree. Right? This computer, what I am calling, I can call it as a root, and the last folder, I am calling it as leaf. Right? Based on that, I am mentioning that a tree is a inverted tree. That's it, right? Is it clear for everyone? Yes or no? Yes. So based on this, I will try to introduce some of the terminologies. Some of the tree terminologies. Here try to observe the same thing, this computer diagram, like the hierarchical file system what I mentioned here. Can I able to write something like this? Computer I am naming it as 1, and C I am naming it as 2, D I am naming it as 3, E I am naming it as 4, F I am naming it as 5, and Arjukit I am naming it as 6, 7, 8 and 9. So to avoid the complexity of further explanation, I am just making it as a rename, right? Just giving a short names. So this is also a kind of a tree. Am I right or not? So for example, if I take something like one tree, which 1, 2, let me take something like this, 5, 6, 7, let me take 8, 9 and 10. So this is a general tree of the data structure. So among these, what are the root? What is the root? 1 is the root. And can I say 10 is the leaf? Yes or no? Yes. Similarly, can I mention something like 2 is a child? Yes or no? Right? So, okay, fine. So to make it more clear, I am just taking some terminologies here. First one, node. Okay. So I can start from here. What is a node? Node is simply an element. Node is a kind of element. Each element in the tree. So you can write in the your notes. You can just write examples. 1, 2, 3, 4. Everything, every particular element is a kind of a node. Okay. Next, root node. What is root node here? 1 will be acting as a root node, right? So I can say technically topmost element of the tree. Topmost element of the tree, I can call it as a root node. So for example, 1 will be the root node. Similarly, parent node. What is parent node? Right? So you can define it a variety of ways. A node have child nodes. If a node have child nodes, we can call it as parent node. What is a child node then? If a node has parent node, okay, a node can have a parent. If a node can have a parent, I can call it as a child node. Okay, I can write a node is, I can write in another way. If a node is descendant of another node, descendant means what? Child. If you observe, does 6 is descendant of 3 or not? Right? 6 is descendant of definitely 3. Similarly, can you give us an example? 5 is descendant of 3. Does 3 is descendant of 1? Okay, Namma? So 3 is descendant of 1. So based on that, so tell me, can I say that 3 is parent of 5 and 6? Can I say that 3 is descendant of 1? Or I can say 3 is child of 1? Yes or no, right? So you can call with a variety of ways, depends on the scenario or depend on the requirement. Next one, leaf node. Leaf, or we can call external node. Leaf or external node. So which one we can call it as a leaf node or external node? Okay, a node with 0 children. A node with 0 children, we call it as leaf node. Right? If you observe the 9, is there any children for it? No. Then I can call it as leaf node. Next, internal node. See, these are the terminals are very, very important for further classes. Next one is the internal node. What is internal node? A node having at least one child. Can I say like that? If a node having at least one child, right? For example, can you say that 7? 7 is the internal node? No. Because if it is having at least one node, then it will be act as internal node. If I say in other words, other than leaf nodes are all comes under internal nodes. What is the meaning of leaf node? If a node having 0 children, I can call it as leaf node. So what are leaf nodes here? 7, 5, 9, 10 and 8. Other than these leaf nodes, the remaining all will become under internal nodes. So leaf node, leaf, leaf, leaf and leaf. And other than leaf nodes, everything will become under internal nodes, right? These internal nodes can have more than one child also, but minimum should be one child. Then I can call it as internal node. Next, siblings. What are siblings? So a node or nodes with same parent. If nodes with same parent, I can call it as sibling. So for example, can you tell me any siblings are there here? Right? 5 comma 6 are the siblings. 2 comma 3 comma 4 are the siblings. Etc. These are all the siblings of the tree. Right? In exam, you might expect different kind of questions. How many sibling pairs are there, like that? Okay. Next, degree of node. Okay. Degree of node. What is the meaning of degree of node? The number of children of a node, we call it as degree of node. Number of children of a node, we call it as degree of node. Okay. What is the degree of node 3? Degree of node 3 is 2. Very good. So how many children are there for 3? 5 comma 6 are there. So the degree of 3 is 2. Similarly, what about the degree of 1? Very good. Degree of 1 is 3. So the total number of children of a node, we call it as degree of node. But if general, if you take in mathematics, if you are able to calculate the degree of node 3, which is 3, I think. Have you got this concept anywhere? Degree of 3 is 3 in mathematics. The total number of outgoing edges. Right? So we will be classified into out degree as well as in degree. Okay. If you are not aware of it, then no need to worry. Just for the sake of data structures point, degree of node is nothing but the total number of children of a given node. Okay. Fine. Similarly, you can able to calculate degree of tree. Degree of tree. What is the meaning of degree of tree? So degree of tree is nothing but maximum degree of all nodes of the degree. Maximum degree of, I can say in other words, so to make it clear, maximum value of all node degrees. Okay. So here, if you want to find out the degree of tree, what you have to do? You have to find out the degree of 1, degree of 2, degree of 3, degree of 4, degree of 7, degree of 5, 6, 8, 9, 10. You have to find out all node degrees, and then you have to pick the largest value, which you can call it as degree of tree. Okay. And if you observe the next terminology, edge. What is an edge? Connection between the two nodes, right? If you take here 2 and 7, as there is a relationship, I can call it as an edge. Edge is nothing but connection between the nodes. Connection between the nodes, we can say it as edge. We can introduce some more terminologies. Ancestors. Ancestors means Purvikla. Okay. The elements which are existed before the current element, right? I can say current node to the root node. The elements which are from current node to root node. Can I say like this? Yes or no? If you want to say the ancestors of 6, what are the ancestors of 6? So ancestors of 6 are 3 and 1. Similarly, you can have the terminology descendants. Already we discussed. Descendants means current node to, very good, current node to leaf node, which we call it as descendants. Okay. Is it clear? Next one, level. Level, right? We can say level represents distance from the root node. Technically, we can call distance from root node, we call it as level. Level. Generally, we can say usually we will able to write it as root node starts with 0. Usually root node is at level 0, or sometimes in the exam they might say that it is starting at the 1, right? So in general, this is what we call it as level 0. Level 0. In the exam they might mention the root node starts with level 1. Then the answer will vary. You have to be take care about the given question. So then this one will be what? Level 1, level 2, and this will be level 3. So if the level starts with 0, the next level is 1, 2, 3. If the level starts with 1, you can go for 2, 3, 4 and so on, right? So this is what the meaning of a level, right? In the exam questions, you will get the terminology called level. If the level starts with, so you should not get confused. Next, height of a node. Height of node. Okay, so next we'll try to discuss height of tree. Height of tree. Then we'll go for depth of node. Depth of tree. Depth of tree. Okay. Now, so I just took them at the same time because to avoid the confusion. So depth of river means what? Depth of loth. Okay. How we are going to calculate? How we are calculating the depth of the river? You will try to calculate from surface to the deeper level, right? So depth of node means what? Current node to leaf node. Very good. Current node to leaf node. What is the meaning of current node to leaf node? You have to calculate the depth, right? So how we are going to calculate it? We can say number of edges between, very good, it's nothing but levels only. Number of edges between the current node to the leaf node. Okay. Is it correct? Depth of a node. So you have to. So it is for height. It is for height of a node, not for height of a node. Height of a node is nothing but current node to the leaf node, and depth of a node is nothing but root node to the current node. So don't get confused. So number of edges between the root node to the current node. Root node to the current node. So you can assume it as a kind of surface. Surface is nothing but root node. Okay. Then you have to go beyond. So that's nothing but depth of a node, right? Similarly, what about depth of tree? What is the meaning of depth of tree? Depth of tree is nothing but the, like, we can say largest path among all the paths, right? We can say, for example, you have to find out what? Height of all the nodes. You have to find out height of all the nodes, and then you have to pick the largest value. So I can say it as maximum value among all height of nodes. Have you understood this meaning? We'll try to find out height of 7. We'll try to find out height of 5. try to find height of 6, height of 9, height of 10, height of 8, height of 2, height of 3, height of 4, height of 1. And among all the nodes heights, you will pick the maximum. Maximum, right? So if you observe, this I am writing it as height. Okay. And here I am going to write it as depth. Now, is the depth and height are same or different? Why it is different? It's same. Depth and both are same, right? If you are able to calculate the maximum number of edges between root node to the any one of the leaf node, always it is same. So here also it is saying that max, here also it is saying that max, then depth of the tree and height of the tree both are same. But depth of node and height of a node is different. Depth of a node and height of a node is different. For example, try to take this particular example here. What is depth of 3? What is depth of 3? Depth of 3 is 1. Why? 1 to 3. You have to find out the root node to the 3. Number of edges are how many? Only 1. So I can write here depth of 3 is 1. Okay. What about height of 3? What about height of 3? Height of 3 is 2. How we are getting the 2? You have to find out 3 to the leaf node. 3 to the leaf node. If you take 3, 6, 9, you will get 2. If you take 3, 6, 10, you will get a 2. You have to take again the maximum one. So this is the meaning of height. Right? Try to find out depth of the tree or height of the tree. Both are going to get same value. Okay, now. So these are some of the terms that you have to know. Just think once, and if you have any doubt, let me know. ఆ లైట్స్ అన్ని వెయ్యి బ్యాక్ సైడ్. మా అందరు నిద్రపోతున్నారా క్లాస్లో? వింటున్నారా క్లాస్? ఇది ఆఫ్ చేయండి, బెడిది ఒకటి. ఓకే రైట్. ఈ టర్మినల్స్ అని మీకు అన్ని ఐడియా ఉన్నవే కదా ఆల్రెడీ. So in any terminals you are getting confusion? Depth. Example చెప్పాను కదా క్లారిటీగా. ఏది కావాలమ్మా చెప్పండి చెప్తాను. డెప్త్. డెప్త్ అంటే ఏంటి? హైట్ ఆఫ్ ట్రీ. హైట్ ఆఫ్ ట్రీ అన్న డెప్త్ ఆఫ్ ట్రీ అన్న ఫైనల్గా ఏం ఫైండ్ అవుట్ చేస్తున్నామా? మ్యాక్సిమం వాల్యూ. సో డెప్త్ ఆఫ్ రూట్ నోడ్ అంటే ఎంత చెప్పండి? డెప్త్ ఆఫ్ రూట్ నోడ్ ఈజ్ 0. అవునా కదా? డెప్త్ ఆఫ్ లీఫ్ నోడ్ ఏమవుతుంది? డెప్త్ ఆఫ్ లీఫ్ నోడ్ మ్యాక్సిమం వాల్యూ. హైట్ ఆఫ్ రూట్ నోడ్ ఏమవుతుంది? హైట్ ఆఫ్ రూట్ నోడ్ మ్యాక్సిమం వాల్యూ. అప్పుడు రెండు సేమే కదా. ఎప్పుడు 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 సినారియోస్ ఏమవుతుందంటే డెప్త్ ఆఫ్ లీఫ్ నోడ్ యొక్క వాల్యూ హైట్ ఆఫ్ రూట్ నోడ్ వాల్యూ ఇప్పుడు సేమ్ అవుతుంది. సో ఆ సినారియోలో మనం ఏం చెప్తున్నామంటే బోత్ ఆర్ సేమ్, బట్ ఎలిమెంట్స్ తీసుకున్నప్పుడు రెండు డిఫరెంట్ అయిపోతాయి. ఓకే, ఈజ్ ఇట్ క్లియర్ నౌ? Okay. So for example, if I take something like this, the root node is 1, it's having 2 children, 2, 3, and it's having 1 children, and it's having one more right child. Can I call for 3 left child is what? 4, because it is aligned towards the left side. For 4, right child is 5 because it is aligned towards the right side. Right? Based on that, you can define left child, right child like that. Okay, fine. If I try to write the technical definition of the tree, what is a tree generally? A non-linear data structure. Tree is a non-linear data structure. Non-linear is it contains collection of nodes. It contains collection of nodes. Am I right? Among all these nodes, one node will act as what? One node act as a root node. This is the definition of a tree. A tree is a non-linear structure which is a collection of nodes. Among those, one node act as a root node and no cycles. And we won't have any kind of cycles. Cycle is nothing but what? If I take 1 is a node, 2, 3, 4, 5, and these are connected something like this. So this is nothing but a cycle. From 3 I can move to 5, 3 I can move to 4, 4 to 5, 5 to 3. So I can call it as a cycle. So can I call it as a tree? No, it is not a tree. I can call it as a graph. That we'll see in further classes. Okay. So if I am saying something like a tree, it should not contain any kind of cycles. It should not contain any kind of cycles. I can call it as it should be acyclic. It should be acyclic, right? Based on that, we can able to write various kind of properties of tree. Can you tell me what might be the properties of tree? How many root nodes it might be there? Only one. So there should be only one root node. Any other properties? It should be acyclic. It should be, there should not contain any kind of cycles. Any kind of cycle. Any other? Any other? So we can say something like this. A node can have 0 or more children. A node can have 0 or more children. And there should be exactly only one path between two nodes. Okay, there should be exactly only one path between two nodes. That's it. If any structure follows these 4 rules, I can call it as definitely a tree. Okay. If you are going to get more than one path, what is the meaning of that? There is a cycle. Then we call it as a graph. Okay. We can't call it as a tree. Okay. So based on these properties, I can define various types of trees. Various types of trees, right? Which means how they have classified is, they have classified based on certain properties and certain kind of behavior, properties and its structure. They have classified into various types of trees. Among those, one type of tree is a general tree. General tree means generally any kind of tree will becomes under a normal tree. Any representation will becomes under normal tree. General tree means if I wish to represent more technically, a node can have any number of children. A node can have any number of children. We call it as general tree. Can I call the left side diagram as a general tree? Yes, we can call it as a general tree. Can I call the right side as a tree? No, because first it has to satisfy the properties. Then only we can classify it under different types of trees. Okay. Next, tertiary tree. Next type of tree is tertiary tree. Tertiary means what? 3M, right? A node can have maximum 3 children. If a node can have maximum of 3 children, we can call it as tertiary tree, right? I mean, if you take any node, that node should have a maximum of 3 children. It should not be beyond that. For example, if I say 1, 2, 3, 4, 5, 6 and 7, can I call this as a tertiary tree? Yes, I can call it as tertiary tree, because take the total number of children for 1, 3, maximum 3, for 2, maximum 3, for 3, maximum 3, right? You have to calculate for each and every node, and at the end, among all the nodes, the maximum number of children should not be beyond 3. If it is beyond 3, I cannot call it as a tertiary tree. Okay, so if I take this one, something like 1, 2, 3, 4, 5, 6, 7 and 8. Can I call this as a tertiary tree? No, because at a particular point of time, a node can have beyond 3 nodes. I cannot call it as tertiary tree. Right? Based on this, can you say the definition for binary tree? Right? So if I say something, a node can have maximum or I can say at most number. So at most means what? 0 or 1 or 2 children. A node can have maximum or at most 2 children. At most 2 children. We call it as binary. Okay. Similarly, we can introduce one more terminology called as forest. So in general, in the real world, how the forest look like? More number of trees, right? Collection of trees, we call it as forest, right? Important for the interview, right? Collection of trees, can we call it as a tree again? Collection of trees, can we call it as a tree? No. If you make collection of trees, for all these trees, there should be some root node. Then only we call it as a tree, right? In general, for a forest, there will not be any root node. It's a collection of trees, that's it. So we call it as a forest, but not a tree. Okay. Fine. I hope it is clear for everyone, right? Next, we'll see the more depth about the binary trees. If you understood the concept of binary trees, you can understood any other kind of trees. So what is the meaning of a binary tree? Very good. A node have at most 2 children. A node can have at most 2 children, which I can say that 0 or 1 or 2 children, but not beyond that. We can call it as a binary tree, right? For example, if I take a node 1, which can have 1 child, as number 2, can I write something like this? Now is it a binary tree? Yes or no? Can I say this is a binary tree? Can I say this is a binary tree? Yes or no? Yes. This is what we call it as binary tree. Can I say, is it a binary tree? Right? Duplicates might be existing. Now, can I call this a binary tree? No. So, we can't call it as binary tree. It is not a binary tree. Okay? Fine. So, based on this, how we are going to draw the trees? I can ask you something. For example, you have some 5 nodes. Let's say you have 5 nodes, something like this. let's say you have some nodes. Let me say that nodes as 1, 2, 3. I have taken only 3 nodes for the sake of simplicity. How can we draw the trees here? What are different types of trees are possible? Can I say this? I can able to form a tree with only one node as 1. Is it possible? Yes or no? One node itself is a tree. Can I do something like this? 2. Can I write something like this? 3 or not? Fine. For example, can I write something like this? 3, 2, 1. Can I write? Can I write something like this? 2, 1, 3. Yes or no? Can I write something like this? 2, 3, 1, etc. Is it possible or not? Right? Now the question is here, how many number of structures are possible with 3 given nodes? 8. How many unique structures possible with n labeled nodes? If I have n labeled nodes means what? A node given with some name, right? Suppose for example, in the gate you might get something like this. How many unique structures? How many unique structures possible with n unlabeled nodes? N unlabeled names means what? They haven't given any names, right? For example, if they are saying that there are 3 nodes, how many structures are possible? Can I say this structure is possible? Yes or no? Can I say is this structure is possible? Yes. All are aligned towards the left side. Can I say if this structure is possible? Okay. Any other structures are possible? Any structure, try to define. Observe this structure, think about it. First node to its left side, then for that right. Similarly, can I have something like this? Right side, left side. Any other structures again? Those should be unique, right? It should not be same like among these 5 structures, right? This particular thing. The second one, what I mentioned here is, we call it as left skewed binary tree. Left skewed tree. Why I am calling it as left skewed tree? Because all the elements are arranged to the as a complete left as possible. And this one we will call it as right skewed tree. Right skewed tree. Okay, fine. Meanwhile, tell me, is there any other structures are possible? Just try to draw it for 4 nodes. For 4 nodes, how many you will get? Right? So, these are the 5 structures only possible with the help of 3 unlabeled nodes. Any other you are going to get? No more. Only these 5 are possible. So, if I generalize it, you will get something like 2n Cn by n plus 1. 2n Cn by n plus 1 is the number of nodes, is the number of structures possible with the n unlabeled nodes. Try to substitute the formula for n as 3. N as 3. Then you will get 6c3 by 4. 6c3 means what? 6, 5, 4, 1 into 2 into 3 by 4. 6, 6 cancel, 4, 4 cancel. You will get finally 5. Right? Are you getting only 5 structures or not? So, this is the formula you have to observe. With n unlabeled nodes, 2n Cn by n plus 1 number of unique structures are possible, right? Generally you can derive it, we don't have any time. So I just have drawn the formula directly here. Similarly, if you have three labeled nodes, then how many structures are possible? Right here I have taken this structure, observe, I have took only this structure. What is that structure name? Triangle shape kind of structure. 1, 2, 3, 3, 2, 1, 2, 1, 3, 2, 3, 1, something like that. Can I redraw the structure something like this? 3, 1, 2. Observe, for this I mentioned. Okay, for this I mentioned. Similarly for 1 also, you can write something like this. 1, 3, 2. Right? So total how many structures are possible in triangle shape for the label? 6. Similarly, if it is a triangle structure, how many general unique structures are possible? 5. This one bottom you can check. In general, if it is unlabeled, total 5 unique structures are possible. If it is a label for one structure like triangle shape, how many structures you are getting? 6. For 5 unique structures, 30 you are going to get. So total, the formula for defining how many unique structures are possible with n labeled nodes means 2n Cn by n plus 1 into n factor. 2n Cn n factor. So here 3 factor is nothing but what? 6. Okay. For one structure you are going to get 6 times. For 5 structures total 30. So if you substitute here, you will get 6C3 by 4 into 6, which is 30. Important for the gate terminology. Is it clear for everyone? Right? Similarly, I might add one more question. A tree of height h. Let's say a tree of height h. A tree of height h. A tree of height h. Let me say that for a tree of height h, maximum number of nodes are fit. Maximum number of nodes fit in the binary tree. Have you understood my question? A tree of height h, how many number of nodes are able to fit in the binary tree? For example, a tree of height 1. A tree of height 1. For height 0, how many number of nodes are you going to fit? Only 1. Height 0, only 1. For height 1, how many number of maximum nodes fit? 3m. For a tree of height 2, maximum how many nodes is able to fit? 7. For a tree of height 3, how many nodes? 15 or not? Yes. So here the question is, for a tree of height h, how many nodes are possible? Right? You can generalize it. If it is a tree of height 0, which will be 2 power 0. If it is a tree of height 1, 2 power 0 plus 2 power 1. At level 1, you have 2 power 1. But if they are asking for a height of 1, how many number of maximum nodes are possible? 2 power 0 earlier level plus current level. Similarly, for this level, we can write 2 square, 2 cube, and so on. So which means, for example, for a tree of height 3, maximum number of nodes are possible how many? Earlier levels, 2 power 0, 2 power 1, 2 square plus 2 cube. What is the value you are going to get? 50. So here the question is, for a tree of height h, 2 power n factorial, So for a tree of height h, maximum number of nodes fit in a binary tree. Right? You have to calculate this one. So how they are available here? If it is a height h, can I write something like this? 2 power 0, 2 power 1, 2 square and so on, 2 power h. For height 3, which is 2 cube. For height h, which is 2 power h. Right? These are in geometric progression. Okay, if they are in geometric progression, what is the formula you are going to use? You might forget a into r power n minus 1 by r minus 1. Right? What is a here? A is the first value, 2 power 0, which is 1. R is nothing but relation 2. N is nothing but, how many elements are there here? H or h plus 1? H plus 1. 2 power 0 to 2 power h. So I can write A as what? 2 power 0, which means 1 into 2 power h plus 1 minus 1 by 2 minus 1, which is what? 2 power h plus 1 minus 1. So for a tree of height h, the maximum number of nodes fit in the binary tree is what? 2 power h plus 1 minus 1. 2 power h plus 1 minus 1 is the correct formula. Okay. Okay, a tree of height h, minimum number of nodes are, can I directly write as h plus 1? A tree of height h, how many minimum nodes are possible? H plus 1, right? You can observe, it might be a complete left skew tree or it might be a right skew tree. If you observe, for height 3, how many nodes? 4 nodes. 1, 2, 3, 4. Height is what? This is the only possible solution. Okay. So, these are the formulas very, very important for you. H plus 1, 2 power h plus 1 minus 1, and these are all the things. Is it clear for everyone? Fine. So, based on this, again, we will classify the binary tree into various types of binary trees. Various types of binary trees. Right? The way they are structured, we classify into different types. Among those, one kind of binary tree is full binary tree. Full binary. Full binary means a node can have, in general, what is the meaning of binary tree? A node can have at most 2 children, right? Full binary means a node must have 0 or 2 children. What about binary tree definition? A node can have 0 or 1 or 2 children. But if you take the full binary tree, it must and should have either 0 or 2 children. Right? So, based on that, for example, if I say this example 1, 2, 3, 4, 5. Can I call this as a full binary tree? We call this as full binary tree. For example, now is it a full binary tree? It is not full binary tree because the node 5 have 1 child. It should have to avoid single children. It mustn't should have either 0 or 2. Can it have beyond 2? No, it won't come under at least binary tree also. Right? This is the meaning of full binary tree. Right? If I say this is the full binary tree, then can you able to define some relation between the internal nodes and the leaf nodes? So we'll try to derive some relation between internal nodes and leaf nodes. Do you have idea about the meaning of what is internal node? What is leaf node first? A node which won't have zero children, which have zero children, we call it as leaf node. Other than the leaf nodes, we call it as internal nodes, right? So in general, total number of nodes in the binary tree are how many? Let me take internal nodes as I and the leaf nodes as L. Then total number of nodes are how many? Why you are adding 1 again? Root node, can you call it as internal node? Yes or no? Right? The total number of nodes in the full binary tree are I plus n. Is it correct? Number of internal nodes plus number of leaf nodes. Okay. Can you able to define some relation for edges? Total number of edges. How many number of edges are possible in full binary tree? Is it 2 into I? Very good. It is 2 into I. Because if I am saying some node as internal node, definitely it is having what? 2 children. If I am saying a node if I am saying a node is an internal node, definitely it is going to have 2 edges. It is going to have 2 edges. So if I am saying that I internal nodes are there, it is going to have 2 into I number of nodes. So which represents the total number of edges. Can you say in other form? Total number of edges. In other form, can you say? Total number of nodes. Good, right? Which is total number of nodes. Total number of nodes minus 1. So total number of nodes minus 1. Total number of nodes are how many here? Total 5, right? How many edges are there? 4. So is it correct or not? So I can write either total number of edges or total number of nodes minus 1 or total number of edges equal to 2i. Right? If you are able to equate these two, what you are going to get? Can you say 2i? 2i is equal to total number of nodes are how many? I plus L minus 1, right? I is equal to L minus 1. This is the relationship between the number of internal nodes and the leaf nodes. I is equal to L minus 1, or we can say L is equal to I plus 1. Very, very important again for the gate perspective. So you won't get any simple question. So damn sure you won't able to answer the gate question from this topic. That's for sure. ఓకే, అంత డెప్త్గా వస్తుంది క్వశ్చన్ అయితే. మన లక్ బాగుంటే బేసిక్ క్వశ్చన్ కూడా వస్తుంది ఒక్కోసారి. బట్ మనం ప్రాక్టీస్ చేయగలిగితే, మన థింకింగ్ కరెక్ట్గా ఉండగలిగితే యూ విల్ ఏబుల్ టు ఆన్సర్ ఇట్. ఎగ్జాక్ట్ సార్ ఈ ఫామ్లోనే వస్తుందంటే నో. ఇలా రిలేషన్షిప్ని మనం డిఫైన్ చేయగలిగితే దెన్ ఓన్లీ యూ కెన్ ఆన్సర్ ఇట్. అంటే మనం థింకింగ్ చేయగలగాలి కరెక్ట్గా. సో దిస్ ఇస్ ద రిలేషన్షిప్ బిట్వీన్ ఇంటర్నల్ నోడ్స్ అండ్ ద లీఫ్ నోడ్స్, రైట్? సో వన్స్ యూ అండర్స్టూడ్ దిస్, సో విల్ గో విత్ further other types of binary trees. We call it as complete binary tree. Complete binary tree. What does the meaning of complete binary tree means? So if I am saying that it is a kind of a complete binary tree, all n minus 1 levels, all n minus 1 levels of binary tree completely filled, and last level elements should be as left as possible. This is the definition of a complete binary tree, right? Which is a binary tree. It can have 0 children or 1 children or 2 children, right? For example, if I say 1, 2, 3, is it a complete binary tree? Yes or no? It is a complete binary tree. 4, 5, 6. Is it a complete binary tree? Yes, ma. Right? So this is complete binary tree because always you have to cross check the n minus 1 levels. The n minus 1 levels should be completely filled. Should be completely filled means what? It should have to satisfy the formula 2 power h plus 1 minus 1. Which means what? The total number of nodes at all levels. This formula has to be satisfied. 2 power h, I mean all n minus 1 levels should be completely filled. And what about the last level? Those should be as left as possible. Then only you call it as a complete binary tree. This is important for again heap tree sum. So for example, if I say the same structure 1, 2, 3, 4, 5 and 6. Is it a complete binary tree? No, it is not complete binary tree. Why I am saying it is not complete binary tree? The last level elements should be as left as possible. But if you observe here, there is some gap between the elements. So we won't call it as a complete binary tree. Okay, fine. Next type of binary tree, perfect binary tree. Perfect binary tree. So perfect binary means it has to follow now the formula 2 power h plus 1 minus 1. So I can write as at last level, you can write more technically, at last level I, we should have how many elements? 2 power I plus 1 minus 1. At last level means what? H. At level height h, it should be 2 power I plus 1 minus 1. Which is nothing but this one or not? This particular green color diagram. So this is nothing but perfect binary tree. Similarly, we can write some other kind of trees, balanced binary trees. Balanced binary trees. So balanced binary means the height difference between, you can write height difference between left subtree and a right subtree. Right subtree should be minus 1 or 0 or plus 1. Again, I will take this definition in further units, but as we are trying to discuss about different types of binaries, I just have given clear idea. Balanced binary means the left side and the right side subtrees are going to be balanced, right? So now observe what is the difference between height difference between the one for one, for this one. What is the height difference? What about the left subtree height? Left subtree is nothing but what? This entire part. What about the right subtree? What is the height of the right subtree? Height of right subtree? 2. Height of right subtree is nothing but what? 3 or 6, which is 1. What about height of left subtree? 1. 1 minus 1? 0. Right? So, which is balanced. So, you have to remove this. If I want to make this as a subtree, you have to remove these edges somewhere. Okay? Subtree is nothing but any of the descendants. Right? So, left. Fine. Next, expression tree. Expression tree. If a tree expresses, if a tree is able to express an mathematical expression, we can call it as expression tree. For example, if I say a plus b into c plus d, this mathematical expression I can able to represent in the form of a tree, which is very, very useful. A plus B, C plus D, then final result is going to be multiplied. This is what we call it as expression tree. Okay, so based on that we can say different types of other trees also, like binary search tree is there, binary search tree, AVL tree. These are all the things that we will discuss in further class. Right? Is it clear for everyone? Various types of trees, various types of binary trees. Okay. So do you have any doubts so far? So do you need break? Break kavala? Okay, we can take break.